this is Mr. Murray, and we're talking about light. Fortunately for you, I'm not going to be singing about it, but here we go. Some things about light. One is that light travels at the speed of light, but it also travels at different speeds depending on the medium. All right, and the medium is just what the light is going through. When we say the speed of light, we're usually talking about if it were traveling through a vacuum, then that would be the speed of light. And that's what we talk about, 300,000 meters per second. Okay, give or take a little bit, actually 299, but you get that in. And so basically, we're usually talking about if it's going through a vacuum. If it goes through air, it's slightly slower. Okay, if it goes through glass or water or things like that, then it will slow down even more. So the speed of light travel differently. Now we basically would say that all wavelengths of light, all frequencies, travel at the same speed, but technically that is not actually true. Okay, it is slightly different. But for example, when light comes through a window, even though it changes speed a little bit, basically it still looks like it's all together. Okay. And we see white light coming through. We don't see it separating into different parts. But if we were to do a prism like this one here, we have a triangle prism, all right? And a prism is going to bend light twice. First of all, it's going to bend it here, it's going to bend it here. And because the slanted, the triangle shape, it's going to bend it fairly drastically. It's not like a glass lens that's just barely bent. This is a fairly strong bend. Now, normally we'd say light would come up here, and the bottom part would slow down so that would cause it to turn and go almost straight across like so. And then over here, the light would speed up on this side and go down like this. But in point of fact, some of the different frequencies of light will bend more or less. And as it turns out, the lower frequencies, longer wavelengths such as red, will bend less, and the ones with the higher frequencies, like blue, indigo, violet, will turn faster. And so they will actually separate. And when this light hits on the other side over here, we would have red, orange, yellow, green, blue, and then go violet. And so we would have a rainbow showing over here. And we say we separate this into the spectrum over here. And so that's basically what a prism does. It makes a rainbow because it separates the different frequencies. By making them bend drastically and twice in a row, it bends it enough that actually the differences in the bending of each frequency is seen. Most things would not do that. However, occasionally you look at things through binoculars or something with lenses, and if they're not very good lenses, a lot of times you will see kind of a shady color around the edges, possibly red or orange or yellowy kind of. And that's probably because they're not bending the rays right, and you're getting this little color thing. We'll talk about chromatic aberrations later, which also is when you have different lights focusing at different lengths. But you may see kind of a little halo of color around the edge because the red or orange ones aren't bending as much as some of the other ones. But usually it's for a prism. And this is called dispersal of light. When we separate it and make it bend to a point like this, then that's called dispersion or dispersal of light. Okay. Now, the same thing can happen like it's happening here, but it can also happen in nature. And in nature, the most common example of a prism type thing would be a rainbow. And basically what's happening in a rainbow, you have water droplets that are suspended up in the air. Okay? And basically when the sunlight comes in, it is going to be, it's going to refract or bend when it hits the rainbow, or when the raindrop, the first one's going to hit here, going to slow down, so it's going to bend in this direction. Now it's going to reflect off the back of the raindrop. Now some of the light will continue to go through, but some of it will reflect. Now notice reflection, just like any kind of reflection, it's going to be at exactly the same angle as the incoming angle and the outgoing angle. So it's not going to refract or bend any there, it's just going to bounce off. But when it comes back out over here again, okay, this bottom part's going to hit this sunlight first, so it's going to bend it, and it's going to move faster and bend out, and the same thing here in this other one. So once again, you're getting that kind of double bending, fairly drastic bending, turning it back around And the red is going to bend less, so it's going to be down here. The violet is going to bend more, so it will be a little higher angle up here. Okay, but the same thing is you're going to get a separation of colors, and so you would have your red, orange, yellow. Now, so that's not very much of a difference, but keep in mind as these spread from the sky down to your eye, they would spread out a fair amount. Now, if you were down here looking at this, you're only going to see, say, for example, maybe the violet from this one. The red would be here. If someone else was standing below you or closer up, so they would hit their eye level, they would see red from that particular raindrop. So it says, well, how do you see the whole rainbow then if you just see one color from that particular raindrop? Well, of course, there'd be many raindrops up in the sky. And so while you might not, for example, if you're right here, you would see the violet from this raindrop, but raindrops up here might seem to be the red, and technically, there would be other raindrops in here, and you would see the different colors from each of those. And so you would see a band of color. And if you were to draw this up toward the sky, like so. Say you're here. As long as there's raindrops up here, you would see these colors coming to your eye, and you would see a rainbow. Now, someone behind you, technically, would be seeing a different rainbow. They would be seeing the things that were at those angles to their eye. Okay? If you were to scoot up here, these people would see things at that same angle to their eye. But eventually, if there's only rain right here, eventually if you move too far close, then eventually you'd be up here. And at that angle, there are no raindrops. Therefore, you would say the rainbow disappeared because there's no raindrop to refract the colors of light for you to see that anymore. And so in order for a rainbow to happen, though it don't always happen, is one, the sun must be at your back. Okay, it can't be too high or too low. Okay, and it has to hit these at the right angle so that they will reflect back to you. Okay, and so if you're farther back here, you would not see a rainbow because at your angle, there are no raindrops. Okay, and so, and if you look at this, it's kind of like if you put your hand out before you at a certain angle and kind of rotate it in a little half circle. Anywhere along that arc that you would make with your arm would be the rainbow. Okay, technically there would be a rainbow down here if you were to dig a hole and somehow have light come down there. Which brings up the interesting question. If you were up in the sky in an airplane, then it is possible that you could see a whole circle of the rainbow possibly. But on ground, you're always only going to see this top half, and that's why you see the familiar half circle that we think of and associate with rainbows. And this is also, of course, why it's impossible to get to the end of the rainbow. Therefore, you can't find the leprechaun's gold because it's always going to be in front of you at this angle, and there's no way you can ever actually catch up to it then because you no longer see the rainbow once you get close to it. All right, you have to be at that 40 to 42 degree angle. All right, now, lenses are similar to this. Lenses is probably a more common application of this that we tend to think of. The idea of bending or refracting light. Okay, so for example, I'll try that again. All right, if we have this, this is a convex lens. C-O-N-V-E-X. Okay, a convex lens gets fatter in the middle, as you can see here. It's narrower at the end or tapered. All right, right here in the middle of the lens, this is called the Center of Curvature. Okay, and at that exact point, it could be considered flat, but basically all the way from there, it begins to curve in both directions away from that. All right. Now, if light comes through the center of curvature, it will go, since it's basically flat, it will go straight through. Okay. If the light hits up here, though, for example, you can see that the bottom of the wave is going to hit first. It's going to slow down, and that's going to tilt it. Okay. Once the whole ray is underwater, then it's going to raise under in glass. It's going to go straight. Okay, so it's going to tilt a little bit. Now when it gets over here, it still tilts a little bit. The top is going to hit the air first, and it's going to go faster, so it's going to speed up, and that's going to tilt the whole way like this. Okay, and it will eventually cross that one in the center of curvature. The ray of light through there. Now at the bottom, you've got the same thing happening. The top is hitting the glass first, so it slows down, and so it begins to tilt a little bit toward this way. Okay. Now, on the other side, the bottom hits the air first, so it starts to speed up, and that tilts it that direction, and it goes, tilts it up. Now you'll notice right here that they cross. At the point they cross here is called the focal length of focal point. Okay, right there's the focal point. All right, that's the point where they've crossed. If you've ever used a magnifying glass to make a circle of light, to burn a hole in a piece of paper, or possibly to burn an ant, depending on what you were doing and whether you're a boy or girl or whatever, probably, but anyhow, and your cruelty, blah, 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 that is, that's basically a focal point, okay, and it's concentrating all those rays, concentrates all the heat from those rays, and that's why it catches things on fire. Now, the distance from the center of the lens to the focal point is known as the focal length, okay, and basically, the more curved, if you have a really curved light, lens, kind of exaggerated there, okay, it's going to really bend those lights, and they're going to have a short focal length. If you have a long, skinny, barely curved one, then it's not going to bend them much, and they're going to cross way out here somewhere, okay? So the focal length basically depends on the curve of the lens. The more curved it is, the shorter it is, the longer it is not. Now, since we're bringing these light rays together all in one spot, a convex lens is also called a converging lens because we're converging all of those rays of light at the same point. Now, if you view an image with a convex lens, if you get inside the focal length, in other words, you get really close to the object, the way the light travels will make it look as if it were coming farther back, which makes it a virtual image. Okay, not a real image, but it looks like there's this bigger image behind the lens that's bringing it to you, and so it actually magnifies it or makes it look larger. Okay, and so when you get close to an object, it will be a magnifying glass, basically, and that's what a magnifying glass is. However, if you get farther back from the lens, hold it out in front of you, and you get outside the focal length, then it will make the objects look smaller, and they will be upside down. Okay, and that kind of makes sense because if you have the light ray from the top of an object coming through a lens, it's going to cross, and it's going to come down here, so it's going to be on the bottom side. Same thing over here, it's going to cross, and it's going to become, the bottom becomes the top side, and so you basically flips the image up. It's a real image, but it's also upside down. And this would be movies, projectors of all kinds that we've used over the years and so forth. All these lenses are usually convex, and they flip the image upside down. All right. Okay. Now, the other type of lens we have is a concave lens. Sorry, there had a little stuff on there. But if you look at it, it goes in the middle, gets skinnier in the middle, and is wider at the edges. And so that's why we talk about concave, because it looks like a cave coming through there. In the center of it, you also have a center of curvature, and objects passing through that will go in a straight line. Oh, that's not real straight. Now, the top ray up here will come. The top one would hit the glass first, so that would slow it down, which would make it go slightly up. Okay, when it gets to this side, the bottom's going to hit light first, so it's going to go faster and turn up to the top, so it's going to come up like this. Okay, on the bottom, same thing, but just flip-flopped. At the bottom of it's going to hit the glass first. It's going to slow down, so it's going to turn slightly. And when it gets over here, the top is going to hit the glass first, so it's going to speed up, and it's going to head down, like so. All right, and so this is in a concave lens like this. We call them a diverging lens because they are spreading the light rays in different directions. More on the next.